This is A21 January 09 question 4. One of the equations which describes simple harmonic motion is A is equal to minus omega squared x. State what the following symbols in the equation stand for. So x is a displacement from a fixed point. A is acceleration. And omega is the angular frequency. A loaded helical spring is often used as an example of a system which undergoes simple harmonic motion. The time period t of this system is given by t is equal to 2 pi the square root of m over k, where m is the suspended mass and k is the spring constant, the constant of proportionality in Hooke's law equation. So Hooke's law equation is F equals kx. State the SI base units of the spring constant. So if we have k is equal to F over x, F is kg, m s to the minus 2, and x is a distance measured in metres, and the m's cancel, and we get kg s to the minus 2. Hence show that the SI unit on the left hand side of the equation for the period is consistent with the SI base units on the right hand side. So if I write t equal to 2 pi squared m over k, and t is in seconds, 2 pi hasn't got units, so we're talking about mass, which is in kilograms, over k, which we just worked out to be kg s to the minus 2, and that's all to the power of a half. So the kilograms cancel each other out. You're left with 1 over s to the minus 2, which whenever you bring s to the minus 2 to the top, it becomes s to the 2, and it's a half to the power of a half. So s is equal to s as proved. Part C, a baby bouncer is a light harness into which a baby can be placed suspended by a vertical spring. So you put the baby in here. The length of the vertical string is adjusted so that when the baby is in the harness and the spring is fully extended under his or her weight, the baby's feet are a few centimetres from the floor. So if I just draw the baby's feet there. An adult starts to vertical oscillations by pulling the baby down in the harness and releasing the baby. The baby can amuse him or herself and take exercise by kicking the floor to continue the oscillations. The oscillations die away quickly, and to keep them going the baby has to keep kicking the floor at just the right moment. The arrangement can be modelled using the equation for the loaded helical spring. Here m is the mass of the baby in harness and k is the spring constant of the vertical spring. Part 1. The spring constant is 130 SI units and the mass of the baby is 7.5 kilograms. Show that the period of vertical oscillations is about 1.5. Now the equation t equals 2 pi the square root of m over k isn't on your syllabus anymore, but because they've given it to you, there is a chance they might give it to you again and ask you to use it. And so we'll just put the numbers in, 2 pi the square root of m over k. That's 2 pi the square root of 130 over k, which is, sorry, that's the other way around. It's 7.5 over 130. And that answer comes out to be 1.509 or 1.51 seconds. So it's about 1.5 seconds, and that's correct. State the name that is given to oscillations that die away quickly. And those are damped oscillations. Describe how the loaded helical spring system in a school lab could be made to show oscillations that die away quickly. State how your modification achieves the effect. So what you could do, you could, if you have your spring, you could add a piece of card like that, and there's the rest of the spring, and it is perpendicular to the direction of the motion up and down. So you could add a piece of card with a wide surface, large surface area at or perpendicular to direction of oscillations. The other thing is, or you could place the spring in water. And I suppose you could say that increases air resistance. whereas this increases resistive forces. On the spring. So that's an or. So they're looking for what do you do and what is the effect. So either of those, you could get 2 marks for either of them. That one or that one. State the name that's given to oscillations such as those are kept going by the baby kicking the floor. They're called forced oscillations. The baby finds that by kicking the floor at a certain frequency, the amplitude of the bounces can be made to increase to a maximum. State the name that is given to this effect, and the name is resonance. Use the data given, find the frequency that is most effective in producing it. So in C part 1, which was over the page, if you just go back there. So in C part 1 you've got the spring constant, the mass of the baby and the period of oscillations, and that's what you can use to get the frequency. So frequency is 1 over T, which is 1 over 1.5, and that gives you 0.6, well I used 1.51, the number that I had worked out, 0.665 or 0.67 Hertz. The baby's cousin of mass 6 kilograms comes on a visit and is placed in the bouncer. Calculate the frequency at which this child must kick the floor to produce the largest amplitude of oscillation. So using the equation again, T is equal to 2 pi square root of m over k. And this time the mass we're going to put in is the 6 kilograms, the same spring constant, and that gives you 1.35 seconds. So therefore frequency is 1 over T, and that's 1 over 1.35, and the answer is 0.74 Hertz.